All right, guys, welcome to our new unit, Unit 7. It's our last unit of the year. Hopefully we can finish it by the end of the month, and then we can start up our AP review for our AP exam, which is in the first or the second day of May, I believe. Just want to let you guys know that in this unit, having a graphing calculator is crucial. Almost everything we do is going to be done on the calculator, and a lot of the problems you can't even do it without a calculator. So hopefully you guys haven't procrastinated too long and you've had a calculator this whole time and you're familiar with it. We're going to be doing a lot of calculator work. Now, what is Unit 7 all about? Well, so back in Unit 2, we talked about the rules for integration. Just how do you find an integral using, the basic rules. It's like the opposite of a derivative. Then Unit 6, we talked about, so what does an integral mean? In Unit 7, we're really looking at how are integrals used. What do they help us find? And so there's basically three things that we're going to be looking at that integrals help us find. Topic 1 is what we call net change. We're going to spend 4 days on that, approximately. It might have changed, but 4 lessons approximately on net change. You'll know what that is, hopefully, by the end of the day. Topic 2, we're going to talk about area. In topic 3, we're going to talk about volumes. And so integrals can help us do these 3 things. So let's go ahead and jump into lesson 1 here. Lesson 1 is our first lesson on net change. So by the end of the day, hopefully you'll be able to understand how an integral can be used to find net change, which is basically the amount of change that takes place over a given period. And I just want to warn you before we get started today, today's lesson is going to be a little bit different in that usually I don't talk too much until I talk a little bit and then I give you some practice right away. This one's going to have a lot of front loading, a lot of me just developing the concept at first before we even get to any examples. So the first 30 minutes is really just devoted to developing the concept, and then we're going to start jumping into some examples after that. So make sure you take really good notes, pay really good attention, and be thinking as you listen to my lecture for the first 30 minutes, and that'll help the examples make a lot more sense when you get there. I do not just encourage you to just fast forward through this part because you'll be totally lost on everything if you do. So that being said, let's get started. So before we begin, I'd like you guys to pause the video here and see if you can answer this question. So pause the video here and see if you can answer this question. And when you unpause it, we'll go over the solution. Okay, so as you guys can see, I'm giving you the average speed of the bicyclists and a time period at which he's going that speed. So on the time period from 0 seconds to 2 seconds, the bicyclist is going a speed of 3 meters per second. Now, how do you find distance? Well, hopefully you guys know that distance is equal to speed multiplied by time. So for this first interval, we're traveling for a total of 2 seconds, and we're going a speed of 3. So the distance that the bicyclist traveled on that interval would be speed times time, which is 6 meters. Okay. Now, on the next interval, he's going faster, 6 meters per second, and he's doing that for the next 3 seconds, from 2 to 5. So his distance on that interval would be 6 times 3, which is 18 meters. And then finally, for the last 5 seconds, he's going 10 meters per second, so his distance would be 10 meters per second for 5 seconds, makes a total of 50 meters. And the question is, how far did he travel overall? Well, you could just add all these up to get your total, which would be 68 plus 6, which is 74 meters. So basically, he went 74 meters in 10 seconds. Okay? And so that's our answer. So I want to graph this, and I'd like you guys to do the same thing. So what we notice is that for the first 2 seconds, he was going 3 meters per second. So that the velocity, we're going to just call that speed for now. So his speed was 3 for the first 2 seconds. So from 1 to 2, he was going a speed of 3 meters per second. And then on the interval from 2 to 5, he was going faster. He was going 6 meters per second. So starting at the second time, all the way up to 5, he was going 6 meters per second. And then finally, on the last interval from 5 to 10, he was going a total of 10 meters per second. Now, what I want to show you guys is that something kind of interesting comes out here. Something that should maybe look a little familiar. We've got 3 rectangles. The area of the first rectangle is 2. The area of the next rectangle is base times height. 3 times base would be 18. And the area of the next rectangle will be 5 times 10, which is 50. Well, those 3 numbers should look awfully familiar. Those are the numbers we just had on the last slide. The base tells me how long he was driving, and the height tells me how fast he was going. And when you multiply those, you get the distance. So it seems like distance is area under the curve. All right? And so now we have a new principle here. If you have a velocity function the area under the curve tells you the distance. Now this is only partially true. But good enough for now. And I'm writing that now because if you're writing this in your notes, I want you to be aware that this is a true statement, but it's only partially true, but it's good enough for now. We'll kind of delve into the details about the details of that a little bit later. But for now, what I want you guys to know that is if you have a velocity function, the area tells you the distance. And so now this is, let's say that f prime represents the velocity of a function. The area under the curve, though, can also be represented by an integral. And let's define that as a new function. We'll call it regular f. Oops, too much. All right? We started at 0 seconds and we went to 10 seconds, right? So, but we'll just go ahead and put a and b for now. But basically, if you integrate the velocity, the result is the distance, right? Now, as an interesting side note, you don't need to write this on your notes, but just as an interesting side note, you guys remember a while back, I think it was in unit 4 or 5, I think it might have been 5. I think it was 4 actually. We talked about something known as the position function, right? And the derivative of that gave us the velocity. This is the same concept, we're just working backwards. Here, if we start with the velocity and we integrate it, we get the position, how much the distance changed. Here, if we start with the position and take the derivative, we get the velocity. It's just going opposite directions. So those two concepts are just inverses of each other. Just want to make that known to you, but you don't need to write that in your notes because we're not talking about that right now. So now I worded this in such a way that to connect it to our word problem, but now I'm going to word it in a more general format. So basically then, the integral of a derivative, we'll just say the integral of f prime tells us how much f is changed over time. this is what we call the net change. So if you integrate a derivative, the result tells you how much the antiderivative has changed over that time period. My time period in this case was starting at 0 seconds and ending at 10 seconds, and that's what goes here. And if you integrate the speed of your bicyclist, that tells you how much his position has changed over time. So the integral of a derivative tells us how much the antiderivative, f, has changed over time. And we call that net change. So that was the informal discussion to help you kind of connect the concept yourself from a word problem there. But now let's kind of formalize this a little bit. Okay? So first of all, I'll explain this title up here in a minute. For now, we're going to focus on net change. So first of all, let's start here. Make sure you guys are taking notes with me here. This piece right here is what we call a derivative, right? But it's also known as a rate of change. Rates of change usually have some kind of unit associated with it, which is a unit over time. You know, like feet over seconds, or meters per second, or miles per hour. Rates of change usually have some measurement of unit over some period of time. So those are the units of a derivative. Now what we just talked about though in the last slide is that if you integrate this from A to B, where B is your ending time and A is your starting time, what that tells you is your net change in F over the time period A to B. So how much the antiderivative changed over time. So if we know how fast the bicyclist is going and we integrate that from 0 seconds to 10 seconds, that'll tell us how much the bicyclist's position, which is the antiderivative of velocity, how much the bicyclist's position has changed over that time period. Okay, and we call that net change. Now, as you guys know, when you take the integral of a derivative, you get the antiderivative, right? And applying the first fundamental theorem of calculus, we plug in the top number first and the bottom number second. Okay? Now, remember, if this is the velocity function, then this would be the position function. And this time here is the ending time. So if you plug the ending time into the position function, that's going to tell you the bicyclist's final position. And if you plug in A, which is the starting time, into your position function, that'll tell you the bicyclist's starting position. Now, if you subtract the final position from the first position, wouldn't that tell you how much his position has changed over time? In other words, it will tell you the net change. And you guys might think, well, Mr. Bailey, you already wrote that over here. I did. And that's because these two halves are equal. This equals this. So if the left side is the net change in position over AB, then so is the left side. It's just different ways of writing the same thing. Okay? So that's all of our information. I want you guys to be aware that this is a derivative, which is a rate of change, and it has some kind of unit over time as its units. This is the ending time, this is the starting time, and when you integrate it, it becomes the net change in the antiderivative over time. I also want you guys to be aware of the fact that this is equivalent to this because of the fundamental theorem of calculus, where this represents the final amount, this represents the starting amount, and it is also just another way of finding the net change. Okay, now let's talk about the units a little bit though. Whenever we did our integral, going back to our bicycle problem, remember how we multiplied the speed times the time, and that told us our distance? Well, speed is like our rate of change, so that was a unit over time, right? But we multiplied that by time, and so these cancel. So after we did that, we got a distance, which was just the unit of measurement, like meters or feet or whatever. So when you integrate something, it takes the time off of the rate. So in this case then, here's what I would like you guys to add to your notes. I would like you guys to add here that the units will be, this just gives you the original units without the time in the bottom. So for instance, if you take something like a rate that's represented by miles per hour, well, if you integrate it, you're just going to get miles. Or if you take something like feet per second and you integrate it, it's just going to become feet. It gets, when you integrate, it gets rid of the time factor on the bottom. So you can write that down. And the reason for that is because you're multiplying time times a unit over time, and they cancel each other out. Okay? So now I'm going to clean up my board a little bit, and I'm going to rewrite what I just wrote. Another way to write this which is the way we'll be writing it usually. Another way to write this, which will be more useful, is if we take this f of a and add it to the other side, so it'll look like this. Why is that? Well, it's just because of the type of word problems that we're going to be using right now in these units for the next 4 days. Is what does f of a represent? That represents your starting amount, right? What does this represent? This represents the total change, or the net change. And what does this represent? This represents the final amount. A lot of the word problems we're going to be looking at, I'm going to tell you something like, okay, the bicyclist starts here, and he goes this far, so where does he end up at? And that's what we want to find. So it's a lot easier to write it where the final amount is solved for already, but it's really just the same equation where you've added this piece to the other side. But there you guys have it. All right, so now I want to add some more concepts to you. Sometimes we have rates that add an amount, and sometimes we have rates that subtract an amount. And I'll call that rate in and rate out. So for instance, to illustrate that, consider this bathtub I've got here. Let's say that you open the drain and the water is leaking out, but at the same time you have water coming in. Well, this thing down here, we know that the water is coming into the pool and or the tub, and we also have water coming out of the tub at the same time. Now, that rate at which the water is coming into the tub is what we would call the rate in. So I'm going to call that I of t. And I of t basically just tells me how much water is going into the pool at that moment, or the tub. I don't know why I keep calling it a pool. All right, this here tells me the rate out, which I'll call O of t. So we have two different rates, and they're working against each other, right? One is trying to add water into the tub, and the other one is taking water out of the tub. So that's what we call rate in and rate. Where'd my tub go? There we go. All right. So we have rate in, which I'm going to call I of t. You know, maybe it would have units like, I don't know, cups per minute. We have rate out, that, let's say that's also being measured in cups per minute. Well, since they're working against each other, we have a net rate. In other words, we can put these together to get a total rate. So let's go ahead and call that N of t. The net rate would be how much is going into the pool or the tub minus how much is coming out of the tub. If you put those together, then you can find the net rate. And that's also in cups per minute, let's just say. So, you know, let's say water's coming into this bathtub at a rate of, I don't know, 30 cups per minute. And let's say it's coming out of the bathtub at a rate of 20 cups per minute. Well, if it's going into the bathtub at 30 and there's water coming out of it at 20, then overall, would the water level be increasing or decreasing? It would be increasing because the water's coming in at a faster rate than it's leaving. And the overall rate of change would be 10, because while we're adding 30 every minute, we're also losing 30 every minute. So altogether, we're getting a net increase of 10 per minute. And so that would be my net rate. So if you take the rate in and you subtract from it the rate out, then you get the net rate. Now, let's take this concept and let's marry it to what we talked about a second ago. What happens if I integrate this rate? What would that tell me? Well, if you integrate a rate, then that tells you the total amount of water that would be going into the bathtub on some time interval A to B. So if this is how fast water is coming into the tub and you integrate that, that's going to tell you how much water actually went into the tub over time. Okay, my time intervals from A to B. So, and as you can see, if I'm just talking about the amount of water, it's no longer cups per minute. Now we're just talking cups, right? Because you take your rate, how many cups per minute is coming into the pool or the tub at that time, and if you do that over a certain time period, you multiply it by time and it cancels out the time. You're just left with cups. Okay? And this, what would this tell us then? What would the integral of O tell us? Well, that would tell us the amount of water that's been drained from the tub. And that would also be in cups. If this is the rate of change at which the water is leaving the tub, the integral of that will tell you how much water has left the tub over at that time period from A to B. Well, if you know how much water went in and you know how much water went out, how can you find the amount of water overall after that time period? Well, you would just take this number and subtract this number from it. It'll tell you how much water overall was the tub increased by on that time period. Okay, and that's what we call net change. So if you take both rates and combine them so you have a net rate and integrate that, that's going to tell you the net change in the amount of water in the pool over time. I'm just going to say pool. I just keep saying pool. and that's also going to be in cups. Okay, so I've created a little table here, and I'm going to formalize it on the next slide, but here it is. We have 6 things. We have a rate in, a rate out, and a net rate. And when you integrate those, you get an amount of water added in over time, an amount of water taken out over time, and a total change in the amount of water in the tub over time. Okay, and so that's what we call rate in, rate out, and net change. Okay, so that's a lot of work, but let's go ahead and say that, let's say that we started with 100 cups already in the pool, in the tub. So at time equals 0, let's say I started with 100 cups in the bathtub already, and I wanted to find out how much was left at the last point in time. Well, I can find my final amount, which I'll just call that F of B, right? That's my final amount, is equal to my starting amount, which earlier we called that F of A, right? My starting amount, and I can add to it the net change, how much overall the amount of water changed over time. Right? So if you take your starting amount and you add to it your net change, I'll tell you your final amount. So maybe this will tell me, okay, after that certain amount of time went by, we ended up adding 500 cups to the tub. So if I started with 100 and I added 500, then my final amount will be 600, right? And so that's the formula we're going to be working with a lot today. So I'm going to take us to the next slide where I've formally written all these things out for you. All right, and so this is just I'm going to rewrite it now. I'm just not going to include the whole chat about the bathtub. So we have a rate in, which I'll call I. And rates, as you guys know, are always measured in some kind of unit over time. It could be any unit. It could be meters, it could be feet, it could be eggs, it could be people, it could be anything over time. Then we have a rate out, which I'm going to call O of T, and then we have the net rate, which is their difference. You always subtract the one that's going out. The one that's going in is a plus, right? If you integrate the I of T on the interval from A to B, that will tell you the total amount that was added over time. If you integrate the amount, the rate of change in going out over time, that will tell you the amount that was lost over that time period. And if you put those two things together in a common integral, then you get the net change in the amount over that time period. And the units for this row are all just the units with no time on the bottom, because when you integrate, you lose a time factor on the bottom. And finally, we have our integral formula, our net change formula here. We have f of x, which is going to be equal to f of a plus the integral from a to x of I minus O dt. Okay? And hopefully you guys know what all these parts are. There's actually a homework problem where you're asked to label what each piece means. So if you get stuck on that, then you'll want to come back to this. But here we go. This is the final amount, which is equal to the starting amount added to the net change. The A and the X represent the time period, where A is the starting time, X is the final time. And the I represents, as we see up there, the rate in, and the O represents rate out. Okay, so this is a very important chart. I would definitely, this is like the main chart that we're going to be using today. Everything else was just kind of leading up to this. So now that we've done that, we're going to go ahead and jump into some problems now. All right, so let's go ahead and begin here. Example 1. The rate at which rainwater flows into a drain pipe is modeled by the function R, and here it is. And this water is being this rate is being measured in cubic feet per hour. So this is how much water is being added into the drain pipe per hour, can be found by using this function here. And T is measured in hours. So the pipe is partially blocked, allowing for water to drain out the other end at a rate modeled by this. So we have water also coming out of the pipe, and this is how fast it's coming out of the pipe in cubic feet per hour. And they tell us that at the beginning of our story problem at t equals 0, there's already 30 cubic feet of water in this pipe. And so our first question then is to identify what is the rate in function. We have two functions up there. One of them is a rate in and one of them is a rate out. Which one is a rate in? Well, hopefully you could tell it's this one, because that tells us that rainwater is flowing into the pipe at that rate. So this is how quickly the water is going into the pipe. So I'm just going to put R. I'm not going to write out the whole thing. I'm just going to put R. R, me mateys. I had to do it. Sorry. Okay. What is the rate out function? The rate out function is the other one. This one tells us how fast water is leaving the pipe. D of t is my rate out function. Find R of 5 and using the appropriate units, interpret your results. Find R of 5 and using the appropriate units, interpret your results. R of 5 would mean we're just plugging 5 in. Okay? And now this is where we're going to start using our calculator a little bit. Okay? Like I said, most of Unit 7 we're going to be using calculators. So the first thing I'm going to do is I'm going to put my functions into my calculator here. So I'm going to push y equals, and I'm going to type in my two functions that I'm given. All right? So my first function is the R function, and I believe that one was 20 sine of x squared divided by, I forgot, 35. There we go. And I'm going to also go ahead and put in the other function. Now it's important you remember which one's where. So y1 is my R function, and y2 is going to be my D function. The D function is 0.04 t cubed plus 0.4 t squared plus 0.96 t. Okay? And that's it for now. So we're going to come out of there. So push second and quit. So we've stored our two functions in there. And what you want to remember here is you want to remember that R is equal to the y1 function and D is equal to the y2 function on my calculator. That's going to come in handy. Now, we just left off by asking ourselves to find R of 5. Now, we could have tried to do that by hand, but we want to use our calculator. Now, before we begin, you got to make sure your calculator is set to radians. That's very important, especially anytime you have a trig problem like we do right now. So if you go check it, push mode, and make sure that radians is highlighted. If it's not, you're going to get all the wrong answers. All right, so now I'm ready. How do I find R of 5 using my calculator? Well, hopefully you guys know this, but I'll go through it again. We're plugging 5 into the R function. So I want to do y1 of 5, basically. So that's what I need to type in. How do I do that? We do vars. We go over to y vars. We push 1 for function. We're going to choose y1 because I want my R function. And then I'm going to put 5 in right next to it there. And that gives me 13.102. Remember, you always round to the nearest thousandths place, which is the third number after the decimal. Okay, so that being said, let's come back to our slide here. And I just found out that it was 13.102. But we want the units, and we want to interpret it. Okay, so first of all, notice that it's positive. That means it's increasing. That means that the amount is increasing. Second of all, notice that this is how fast it's increasing. And third of all, notice the units are cubic feet per hour. Okay, so, and this time, this thing that we just plugged in here, that's the time. That's t equals 5 hours. So my interpretation, as I've told you guys in the past, your interpretation has to have three things. It has to have the units of your input, the units of your output, and then the context. And so here's the proper interpretation of that result. We would say that at, let me use black. I don't like this green color here. Will it let me change my color? At t equals 5 hours, the rate at which water flows into the drain pipe is 13.102 cubic feet per hour. And that's what that means. That's what the result means. So at t equals 5, the rate at which the water is being added into the pipe is 13.102 cubic feet per hour. All right. Let's go ahead and move on to the next question. All right, moving on to part D. Now we want to find D of 5. And we're going to pretty much be doing this the same exact way we did the other one. It's just that we're using the D function, which you remember on our calculator is the Y2 button. So let's go ahead and do that real quick. So now I'm going to push vars, y vars function, and this time I'm going to click 2 for y2 because that's my D function. I'm going to plug in 5, and there's my answer for that. I get 19.8. So D of 5 is what we would get by plugging 5 into this. You don't really need to show the work like I did on the last one. You can just put D of 5 and just put what the calculator gives you, though. And what does this mean? Well, this is the time. So once again, T equals 5 hours. And we know the units for the output of D, it's cubic feet per hour. But what is it? Well, remember, this is how much water is being drained out. So if I wanted to write my interpretation of this, you would have to include the input units, the output, and its units, as well as just in the context of the problem, what does the whole thing mean? So here we go. This means at T equals 5 hours, water is draining from the pipe at a rate of 19.8 cubic feet per hour. Got all three things in there: input and units, output and units, as well as the context of the story about water being in a pipe. All right, let's go ahead and move on to our next question. Now they want me to find R of 5 minus D of 5. All right, now luckily I already found these two things, so I don't have to go back to my calculator, although you could just type this into your calculator and it will do it for you. However, we already know what R of 5 is and what D of 5 is. For that one we had 13.102, and for the other one here we had 19.8. And so if I subtract those two things, I will use my calculator for that, I get negative 6.698. Now for this, you're going to want to remember what that is. Whenever you take your input rate and you subtract from it your output rate, what you get is your net rate of change. And if you forgot that, then all you need to do is just kind of go back to this chart right here, and it was the answer that we had right here. If you take your rate in and your rate out and subtract them, you get your net rate. So we want to interpret this. Well, if it's a rate of change, then it still has the same units. It's still cubic feet, right, per hour. Those are my units for the output. And as you can see, the input is still 5, so we're still dealing with the 5th hour. But what does this mean? Well, this means this is the rate overall at which the amount of water in the tube is changing. Okay? Yes, water is coming into the pipe, but it seems to be leaving the pipe at a greater rate than it's coming in, leaving us with an overall rate where the amount of water in the pipe is decreasing at a rate of 6.698 because the rate out is greater than the rate in. So here's how we would interpret this final answer. Input units, output units, as well as the contexts. Here we go. You would say the rate of change, you could say the net rate of change of the amount of water in the pipe at t equals 5 hours is negative 6.698 cubic feet per hour. Now, that's one way to say it. I think they prefer you in the interpretations, though, to word it a little bit differently whenever you're taking your AP exam. I think that they would prefer this. So what they like about this method more is that they know that since this is a negative rate, if you write it like this, they know that you know that it's decreasing, right? Because if your rate is negative, that means the amount of water in the pipe is decreasing at that point. And so they do prefer it worded this way instead. Now, would they give you credit for this up here? I think they might. But I know for a fact, I've heard explicitly that they do prefer it this way. So this is the best way to do it. So just know that if it's a negative rate, the best thing you can do is to state whether it's increasing or decreasing at that point. If it's negative, it's decreasing. If it's positive, it's increasing. Okay. All right, let's go ahead and continue on with the next one. Next question is asking me to find the amount of rainwater that flows into the drain pipe. Well, so this is asking me to find the amount that goes in. On our little chart, we talked about how you can find the total amount that goes in over a certain time period. The way you do that is you take the rate at which the water is going into the pipe and you integrate it on the interval that they want. So once again, from here, though, I'm just going to use my calculator to answer this, but I want to do the integral of my input. Now, actually, I should not use I of t here. That's what I used in my chart. But here, what we're dealing with is we're dealing with r of t. There we go. So you want to use r, not I. Okay, so let's go ahead and go to our chart here, or our calculator, and let our calculator do all the work for us. Do you love that? Really quick. Okay, so how do you do an integral? You push math, you push 9, you type in your lower limit, your upper limit, And we want to put the R function here. And remember, on my calculator, that R function is y1. So I'm going to push vars, y vars, function in 1, dx, enter, done. And remember, we always round it to the third decimal place, so it's going to be 22.956. 22.956. Now, 22.956 what? Well, as you guys remember, the units for R of t was cubic feet per hour. But since we're integrating it, that means you're multiplying it by a time factor, and so those cancel, and so there's your answer. It's just cubic feet now. When you integrate it, you lose the time factor. So that's the amount of water that flows into the drain pipe from the 0 hour to the 5th hour. So over a 5-hour period, it added in that many cubic feet of water. That's what that means. I bet you guys could probably predict what's coming up next. Let's go ahead and take a look at the next question here. Find the amount of water that flows out of the drain pipe on that interval. So in that case, we're looking for the integral from 0 to 5, but this time of dt, the rate out. If you integrate the rate at which the water is leaving the pipe over the time period, then that will tell you how much water overall left the pipe on that time period. So once again, we're going back to the calculator to let the calculator do the work for us. So we're going to push math again. We're going to push 9. We're going to put 0. We're going to put 5. And this time I want the d function, which on my calculator was saved as y2. So we're going to go to y vars. And this time I'm going to push 2 to select y2. And that's 34.917. 34.917. And once again, the units of the rate of change in which it was going out was cubic feet per hour, but we're multiplying it by time when you integrate it, and that leaves us just with cubic feet. And so once again, this just means that's how much water left the pipe. So the pipe started with 20, well, the pipe had 22 added in, according to our answer from part F, but over that same 5-hour period, 34 cubic feet left the pipe. So more water left the pipe than went into it on that first 5-hour time period. Find the net change in the amount of water that went into the drain pipe. Now I'm going to do this problem in 2 different ways. I'm going to do this problem in 2 different ways. One way is the formula method I shared with you. The formula method I shared with you is to find your net change. You're going to integrate the rate in minus the rate out, which in this case is d. So if you take the net rate and you integrate that, that'll tell you the net change in the amount of water over that time period. So I'm going to start it that way. There's a much easier way to do this, but I just want to connect endpoints here for you guys so you guys can kind of get the basic gist of things. So let's go ahead and use our net change formula here. So it's the integral from 0 to 5 of the rate in, which on my calculator is y1, minus the rate out, which on my calculator is y2, all with respect to x, and I get negative 11.961. Negative 11.961. And once again, this is going to be in cubic feet. What this means, you guys, is that's the amount of water. That's the net change in the amount of water on the time interval from 0 to 5. So in other words, over that 5-hour period, because the rate at which water was leaving the pipe is greater than the rate at which water is entering the pipe, overall that 5-hour time period, the amount of water that was originally in the pipe to begin with decreased by 11.961 cubic feet. Now that's one way to do it. But here's another way. We already found the amount of water that went into the pipe. It was 22 point, let me get my calculator here, I forgot. 22.956. So this was the amount in. And we also found how much left the pipe over that time period. That was 34.917. And since it's leaving, we're going to subtract it. That's the amount out. Well, this is how much went in. This is how much went out. If you just subtract those, you get that. In other words, since more came out than went in, we end up with negative. Now, I don't want you to think, well, wait a minute, Mr. Bailey, you can't have negative cubic feet of water. Well, you got to remember, we started with 30 cubic feet. So we started with 30 cubic feet, and over that 5-hour time period, this much went in and this much came out. So we lost this much from our original amount. So we don't have negative cubic feet of water, but that's how much water we lost from the starting amount, which was 30 cubic feet. Okay, so there's that. Let's go ahead and move on to our next question here. Write an integral function that represents the amount of water in the pipe at time x. All right, so for this, we're going to call this function g. And that g represents the final amount. You don't have to label this like I am, but I'm going to. That's the final amount of water in the pipe at time g. How can we find the final amount of water in the pipe at time g? Well, we'd have to take the starting amount of water, and we would have to add to it the net change in the amount. The starting amount is 30 cubic feet. The net change is given by the integral of my rate in minus my rate out on the interval from 0 to whatever my final time is, x. So this is my function. So you have your g of x, that's the final amount, is equal to the starting amount plus the net change from your start time to your finish time, which in this case is x. And on the inside, we have our rate in minus our rate out. All right, let's go ahead and take a look at the next question. Find how much water is in the pipe at t equals 5 hours. So now they want to know what's the final amount of water in the pipe at t equals 5 hours. All right, so to do that, we already have our function from the last question. This function can tell us how much water is in the pipe at any given time. So if I want to know how much water is in the pipe at 5 hours, then I'm just going to plug in 5. Oh, I forgot this. So my integral now becomes going from 0 to 5. And once again from here, we're just going to transition into using the calculator to answer the rest of the question. So for this one, what I'm going to do is I want to figure out what G of 5 is, right? But to do that, basically what I'm going to type into my calculator is I'm going to type in 30 plus the integral. So here we go. So we have our starting amount, 30, plus the net change, which is going from 0 to 5 in this case. And we do our rate in, which I've stored under y1 minus y2, which is my rate out, and then enter. And that'll tell me how much water is in the pipe at that point in time. All right, and that's 18.039, and that would be in cubic feet. Now, just you know, there's another way we could have found this. I mean, we already knew, for instance, that the net change was something like negative 11 point something. I forgot what it was at this point. And we also know that we started with 30. So if this is how much we lost and this is how much we started with, that's what we get there. So you can use it just using the formula, or you can just kind of rationalize your way there if you understand what all the pieces are that you found. But there it is. So, all right, one more question on this worksheet here. The last one, let me scroll down to it. Okay, so find and interpret G of 5 minus G of 0 using the correct units. All right, well, we just found G of 5. G of 5 was 18.0391. And G of 0, well, you got to understand what G is. G tells us how much fluid is in the pipe, and T is the time. So if the time is 0, how much fluid is in the pipe? Well, that means how much fluid was in the pipe at the very beginning, and that's 30. And so if we go ahead and do 18.039 minus 30, we get negative 11.961. Now that number should look familiar. We saw that earlier today. And what did we call that earlier? Well, we called it the net change. I forget which problem it was, but it was one of our problems that we did. Remember, there's two ways that you could write net change. So if you have a rate, right, and you integrate it from A to B, that's net change. But you can also apply the fundamental theorem of calculus, integrate it and plug in the values and subtract them. And since these two things are equal, this is another way of writing your net change. Now, the key difference, there's something important here though. This also looks like something else that we saw earlier today. It looked like this one. Let me find it here. On this little chart I gave you guys, it looked like this one that I put right here. This is different. First of all, notice that they're, oops, I didn't use R on the notes, though I used O. This is different for two reasons. One is you can see these are different functions. That's I and O, whereas the one that we just saw on the last page was this. So up here we have two different functions being subtracted from each other. One's an in function, one's an out. Down here I have one function at one value being subtracted from itself at another value. So it's the same function on the bottom. So that's one thing that makes them different. Another thing that makes them different is that these are rates. I and O are rates. They're telling you how fast something happens, whereas the one that we're talking about right now, that's a quantity. Okay? So this is the net rate of change, but this is the net amount of change. So that's different. A rate tells you how fast something is changing, whereas an amount tells you how much there is. And so it's kind of easy to get these concepts mixed up because they look a little bit similar, but hopefully you can see the differences there a little. All right. So now let's get our interpretation straight though, right? Because whenever we have our interpretation, we want our input units, we want our output units, and we want to include the we want to include the context of the problem. So these values right here, these are time values. The 5 represents the 5th hour, and the 0 represents the 0 hour. The outcome here is the change, the net change in the amount of water in the tube. So basically what this means is that the total amount of water in the tube has decreased by 11.961 cubic feet on the time interval from 0 to 5. So notice I have my output units, I've got my input units, and then the story problem interpretation, which is the context. Okay. Now another way you could have written it's not as good, but you could have just said it's the net change of G over 0.5. But that's really leaving a lot of information out. This is technically true. It is the net change of G over the interval 0.5. But when we do interpretations, you really want to include the story problem in it. And also, once again, you'll notice that I put decreased by 11.961. I didn't just put that the amount of water in the tube changed by negative 11.961. I'm specifying that negative means that the amount of water decreased because it's negative. Okay, so there you have it. And now you guys get to practice it. Now on the one that I'm giving you, it's the questions on yours is going to match this almost exactly, so you can match each question on your worksheet back to this one to kind of get an idea of what to do. But here's yours. So go ahead and pause the video here and work out every problem, and when you're done and you unpause the video, you will see the solution. So here is a quick shot of all the answers if you want to just check your work. And now after this, I'll go ahead and explain the answers. You don't have to watch all of this, obviously. Just go to the parts that you didn't get right and watch that part. This video is long enough already. But anyway, there's the answer. So if you need to look at it a little longer, go ahead and pause it and look at it, and then fast forward to the parts that you didn't get, if any. And so here we go. All right, so our first question here is, what is the rate in function? And the answer to that is it's E of t, because the word problem up here tells us that that's the function where the customers are arriving. The second question here, what is the rate out function? Well, there's only one other option now, so that would be the L function. All right, part C is asking us to find E of 3 and then to interpret our answer using the appropriate units there. So let's go ahead and do that. So E of 3 basically means I'm going to be plugging 3 into this function up here. Now I'm going to do that on my calculator, and the answer I get is 12. Now we have to understand this is a rate, right? So it's a positive rate, and the units for this are in people per hour. So our interpretation of this would be as follows. At t equals 3 hours, I should have put hours there. At t equals 3 hours, or you could just say at 2 p.m. because if we're starting at 11 a.m., that's 0, then that means that 2 p.m. would be the third hour. So at t equals 3 hours or 2 p.m., people are entering the cafe at a rate of 12 people per hour. So that would be the proper interpretation there for part C. Let's go ahead and take a look at part D now. Part D, we want to find L of 3, and once again, all that means is we're going to be plugging it into this function here and interpreting our results once again. So I have 21, and that's what my calculator gave me whenever I plugged it in, and the interpretation of that would be what you see over here. at t equals 3 hours, that is 2 p.m., people are leaving the cafe at a rate of 21 people per hour. So the rate at which they're leaving seems to be greater than the rate at which they're entering at that time. Our answer to C was only 12, but our answer to D is 21. Let's go ahead and take a look at part E. So on part E, we're being asked to find this. And we already calculated E of 3. We did that on part C here, and we found out that that was 12. We already calculated L of 3. We did that on part D, and we found out that was 21. So if we subtract those, we get negative 9. Now, what is that? Well, they're both of these are measured in people per hour. So this is going to have the same units, people per hour. But what is the interpretation of this? Well, if you look back at our little chart that defines all the functions and stuff, when you do your rate in minus your rate out, you have your net rate of change. So our interpretation would look like this. Now, I wrote the answer in two different ways. The first way is kind of easiest to write. It says at t equals 3 hours, that is at 2 p.m., the net rate of change is negative 9 people per hour. But I like the second one more, and I think the AP readers would like the second one more. I think they would give full credit for both, though. But what I like about the second one is it kind of really does interpret what's going on. Since the number of people entering is 12 people per hour and the number of people leaving is 21 people per hour, that means that the overall rate of change of the number of people in the restaurant at that time is decreasing, or the number of people in the restaurant is decreasing at a rate of 9 people per hour. So I like this one the best because this really shows that you truly understand how these problems and questions relate to what's going on in the word problem. But technically, I believe either one of those would be acceptable. Let's go ahead and take a look at F, the number of customers that came into the restaurant from 11 a.m. to 2 p.m. All right, so they're asking for a total number of people now. They're not asking about rates, so we're not dealing with just E and just L, but they want a total amount. And when you want a total amount, then you're going to be integrating. Now they want to know how many people came into the restaurant, so I would be integrating the E function there. And then since I'm going from 11 a.m. to 2 p.m., 11 is t equals 0 and 2 p.m. is t equals 3. So that means we're integrating from 0 to 3 with our E function. Punching that into our calculator, I would get the following: 105.75. Now that's a number of people. So the total number of people that actually walked into the restaurant from 11 a.m. to 2 p.m. was this many people. Now, it wouldn't hurt to round that to 105 people or 106. Either way is fine because you can't have a fractional number of people. So we could say that or that. It doesn't matter though. All right, let's go ahead and take a look at part G. Same question, but now instead of asking what's the total number of people that entered the restaurant, now they want to know what's the total number of people that left the restaurant. So it's going to be the same thing. We're integrating, but now we're going to be integrating the L function, the total number of people that left from 0 to 3, because we're still looking at the same time interval here. So let's punch that into our calculator and see what we get. And I'm getting 93.375, which once again, you probably just round that to 93 people have left overall. So they've had 105 people enter the restaurant, but 93 people have left over that 3-hour period of time. Okay, let's go ahead and continue here and take a look at H. H is saying find the net change in the number of people in the restaurant from 11 a.m. to 2 p.m. Well, net change can be found by taking the integral of the number of people who have entered and subtracting from the number of people who have left on that same time interval. Okay, now you could punch that into your calculator and you can get your answer for that. So let's do, and I get about 12.375 people. Now notice that it's positive. So that means that on that 3-hour period of time, the population has increased from its initial amount by 12 people approximately. 105 people came in, but at the same time, 93 people left, meaning that we have a net change of about 12 people overall. Okay, let's go ahead and move on to part I here. Part I is asking us to just write a function. It says, write an integral function, and we're going to call it p of x, that represents the number of people in the restaurant at any given time. So the final number of people in the restaurant at any given time can be found by taking the starting number of people, which is 28, and adding to it the integral of the net change. Now, something that's a little bit tricky here that you might have missed is this is not actually the starting number of people. It says that there are 28 people in the cafe at t equals 1. Now, that's not a problem so long as I start my integral at 1. Okay, so you probably put 0 here because we haven't seen too many examples like that today, but basically, whatever t value gives you this number, that's what goes here. So it doesn't actually have to be the first number. It just has to be an output amount that matches this particular time value. Okay, so at t equals 1, which is about 12 p.m., there are 28 people in there. So if we start there and put x here, that will give us a total amount. All right, let's go ahead and move on to part J here. So now the question is, now that I have a function that can tell me how many people are in the cafe at any given time, let's answer that question. How many people would be in there at 2 p.m.? Now we have to remember that 2 p.m. actually means t equals 3 hours. So p of 3 is the total number of people in the cafe at 2 p.m. or t equals 3 hours. So there are 28 people in the cafe at t equals 1, in other words 12 p.m. And we want to go all the way up to 3 and find out how much the population changed over that time period with our net change. And by adding those together, we'll get our final outcome. So I'm going to go ahead and calculate this on my calculator and add 28 to it. And the outcome is 11.6. It just keeps going after that, 11.66666. You could round it to 12 if you want to, or you can round it down to 11. It doesn't really matter. And that's about it. So at that point in time, there would be about 11 or 12 people in the restaurant at t equals 3. All right, last question here. Let's go ahead and take a look at part K. Find and interpret p of 3 minus p of 2. Now, I already found p of 3. I did that up here in part J. So we found out p of 3 was 11.6666, which I'm just going to round to 12 for now. And then we need to find p of 2 now. So I need to repeat what I did on part J. Only this time I'm going to be plugging in 2 at the top there. Now, once again, this is a calculator thing, so I'm going to get out my calculator and do this real quick. Let me see what I get. I get 28 about. So basically, the population didn't really change much during that first hour. That doesn't mean that people didn't come in and people didn't leave. It just means that the number of people that came in and left for those first 2 hours balanced out perfectly. So you ended up with the same number of people that were in as there were at the beginning. But anyway, I ended up with 28. So we have p of 3 was 12. We have p of 2 is 28. And if we subtract those two things, we end up with negative 16. Now, what does that mean, though, exactly? Well, what does p of 3 mean? P of 3 means that's how many people were in the restaurant at the third hour, or you could say 2 p.m. P of 2 means how many people in the restaurant at the second hour, or in other words, 1 p.m. And so what does this mean then? Well, that's basically your net change. That's the change in the number of people in the restaurant from hour 2 to hour 3. We went from having 28 people to only 12. So the population decreased by 16 people. And so the interpretation would be as follows. And there you have it. So Hopefully that was helpful, and we'll get to practice this stuff a little bit more in class. So we'll see you guys then. Have a good night.